you're going to drain the bottle.
But the actuation of
actuation of valves venting the chamber has a
it'll take much, right?
no, it shouldn't take very much. The chamber has a volume of about 20 litres or something, perhaps, if that. And actuating the valves is going to hardly use anything. Right, so important thing, any questions as we're going through, just ask. Questions are good. Right, so I need to familiarise you with the machine to start with. First thing is the vacuum system. So it's fairly simple. The vacuum system is simply a turbo pump which is located on the back of the chamber behind here, which is backed by a diaphragm pump which is outside this area over there. There's a gate valve to isolate the chamber from the pump in between them. And teed into the backing line there is evacuation of this water reservoir and connection to these force compensator bellows. So where's that laser pointer? This is quite an important part of the system, these bellows down here. So up here inside there, well, you can't really point it out, but inside there's a big flexible bellows, which I don't know if you can see or not. Kind of pointing at it there. There we go. That feeds this manipulation system up into the chamber. So that's what enables the lower platen to move around. That's that flexibility to do that. When the chamber is evacuated, that bellows is going to have a tendency to pull up. So to compensate against that, we have these 4 bellows underneath. So there's one there, and then 2 behind them at the back. Those 4 bellows have a volume which is roughly equal to the upper bellows, and they counteract the force. It's not entirely equal, so we're going to see later on when we use the software, we might see negative forces and things like this at certain points, which is as a result of the mismatch, slight mismatch between the force compensators and the upper bellows. But they're there basically to stop, when you pump the chamber down, they'll stop the whole thing from jumping up. So they're quite important. That's pretty much the vacuum system. This is a water reservoir for when we're doing direct bonding. If you leave the wafers under vacuum for a long time, the surfaces of the wafer can become dehydrated. So we have this water reservoir to inject water into the chamber to rehydrate the wafer surfaces, and then you'll get a better bond.
How do we do this with water?
You simply remove this clamp, the reservoir drops off, it's just on a KF16 flange. Fill it up about 50%, half full with DI water. We don't want to fill it up too much. So yeah, about half full with DI water. Then the way to use this system, when we first switch the pump on, during pump down, we can open this vacuum valve. That will expose this reservoir to the backing line, only the backing line, not to the chamber. And the idea of that is it will evacuate the headspace and also degas the water. So when the pressure gets down to say 5 or 10 millibar, which is backing pressure, after that this isn't really doing anything much more, so we can shut that valve off. This is held under vacuum at that point, and then when you want to admit water into the chamber, we can open this vapor valve. That will allow water up into the chamber, and you get a saturated vapor pressure of water, which is 5 to 10 millibar. Is what will happen inside the chamber. We'll come back to that later on when we actually do some bonding. We can use that so you can see it in action, but that's basically the principle of it. Right, yeah, that's pretty much the vacuum system. Manipulator system, so this hole from these slide rails there all the way down, this is what we call the manipulator. This enables you to translate the lower wafer in X, Y and Z directions, as well as rotate in theta direction. So it's a 4-axis manipulator. There's a motor here, and there's another one on the side for driving it in X and Y directions. Then a hydraulic system to drive it in the Z direction. So that will also enable it to apply force up to 25 kilonewtons. The hydraulic system is powered by this motor. and it's attached to a screw pump which is in there, just there. So as that screws in, the motor will slide on this tray down here. So that will screw in, push the hydraulic fluid around the system, and it will actuate this ram here. There's a load cell on top of it there, and that will push this whole central tube arrangement up and down. Lastly, there's a stop valve there, and the purpose of that is to prevent application of excessive force. So that will basically limit the hydraulic force to 25 kilonewtons, or just over 25 kilonewtons. Above that, this valve kicks in, and you end up pushing against the valve rather than pushing further against pushing the wafers further into contact. So that's kind of a safety feature. Optical system. So the optic system is up here, this microscope arrangement. There's two CCD cameras here to view the left and the right. They're viewable from the software in this screen. I'll talk you through the software later. But we have two modes of illumination. We can use visible light to illuminate. That comes through these LED lamps. Or we can use infrared illumination from underneath. That's fed into the chamber. Use infrared light to see through two silicon wafers. Visible is preferable, so if you're bonding silicon to glass, we can use visible illumination and you get a much clearer picture, much better resolved picture with that. But for two silicon wafers, obviously they're visible, opaque, so you have to use infrared light to see through them. No choice in that case. This moves up and down on a rack and pinion system as any normal microscope. We've also got X, Y, and Z kind of fine translation stages on each side.
What's the opening size?
How do you mean the opening size?
So like, there's like
the viewing window.
Wafer.
Yeah, I think there's a viewable area of about, the viewport holes through the Platens are about, I think, 8 millimeters in diameter. So it's very important that when we have alignment marks, they have to be positioned within that 8 millimeter window. In the manual, there are some technical drawings of like layouts for alignment marks, and the measurements, I believe on a 4-inch wafer, they have to be exactly 67 millimeters apart. I can't remember off the top of my head. I'll show you later in the drawing. Yeah, so each camera we've got independent X, Y, and Z fine control. They're powered and they communicate with the PC via this firewire cables, which is fed through there and around to the back. So if I just show you here, we've got toggle switches for visible and infrared light. And we can also independently adjust the gain and the shutter for the cameras to adjust the contrast. So we can adjust those sliders to get a good contrast. And similarly with infrared light, that's illuminated from underneath inside the chamber. We also have a level control for that, so we can adjust the level of the light, we can adjust the intensity, as well as adjust the camera gain and shutter. Okay, nitrogen cooling system, right. Best if I show you that inside the chamber. So to open the chamber, I might as well show you this while we're at it, the front panel controls. We've got two buttons for opening the lid, the rocker switch here, right to open, left to close. Doing that on its own does nothing. You have to also push this button. The idea of that is it forces you to use both hands, which means you can't accidentally have a hand in the way and get crushed by the lid. So that's a sort of a safety feature. So for nitrogen cooling, in manual mode, we can open the nitrogen valve there. That admits nitrogen into the chamber through this ring. That will just spray nitrogen all the way around. So that's for forced cooling. Nitrogen comes in through this port here, through a 1/4 inch tube. The exhaust goes out through the same tube, out of the branch of a larger T-piece, and comes out through an exhaust valve, which is located there. That there is the exhaust valve assembly. So the nitrogen is admitted by a similar pneumatic valve located back here, somewhere we won't be able to see it. That will open when the chamber reaches 1100 millibar. The exhaust valve will open, and then there'll be a continual flow of nitrogen into the chamber through the ring, out through this port and down the exhaust line. So after bonding, if you put your hand under there, you'll feel warm nitrogen coming out. It'll be expelled. There's an option, there's a fitting on the bottom of the nitrogen valve to extract it. So if there's any harmful chemistries or anything going on, you need to extract, there's the option to extract the exhaust. If it's just nitrogen, it doesn't matter. So it's not connected to anything at the moment. External leveling, I'll show you in a minute. Wafer clamp system. Okay, so the upper wafer, to do this, for this alignment to work, the upper wafer has to be held upside down. So when the lid's closed, the wafer's upside down, it has to be held up there so that you can hold the two wafers in separation to perform the alignment. So the way it's held is with this wafer clamping system. So there are two little screws here that are, and the wafer is pushed against those screws by this shuttle assembly. That shuttle is actuated by this handle underneath the lid with a white knob on it. So that,
Like spring?
yes, it is. It's sprung loaded, so that will has a tendency to push back. So to clamp the wafer, we need to push it against those two screws, retract the clamp, then engage it against the edge of the wafer. That it can be fiddly. There we go. So it's a very delicate mechanism, but it only has to hold the weight of a wafer. So it is. It does work.
And you mentioned something about negative voltage, so the glass goes here and
Yes, the glass goes on the upper platen, which is where we apply the negative voltage. That comes through this wire here, and it's fed into this. We call this the support ring. So this ring of metal supports the platen, so hence it's the support ring. We apply the negative voltage to that, so the whole platen and the support ring and this wafer clamp are all charged. They're all sent up to high voltage, to a maximum of 2,500 volts. Generally, for bonding 4-inch wafers, we use 800 volts, so there's plenty of like excess capacity if necessary for whatever reason. It's isolated from the lid. The lid is at ground potential, it's earthed through a wire. It's isolated from the lid through these ceramic plates and also through zirconia balls, which I can't get the pointer onto. There's a little white ball on top of this gear.
yeah.
So there are three, one on top of this gear, one on top of this gear, and one on top of this block at the back. If you bring it up to the top, see just in there, this block has another ball on it. So there are 3 isolation points.
This is on the ground, right?
Sorry?
The other wafer will be on the ground.
Yes, the lower platen is grounded, yeah. So, I touched on these gears here. Now's a good time to explain their functioning. So, the idea of those gears are attached to plugs with a fine thread on them, so that they can lift up and down. And that will enable you to level this entire system. So the leveling is accomplished using these 2 rotary feed throughs. So as we turn one of these, it will turn this spur gear, which will in turn turn that disc gear, and that will lift up or down depending on which way you turn it. And the idea of all that being that we can control we can control the position of these 2 points of the platen. So with that, we can adjust the level to achieve parallelism between the upper and lower platen. The lower platen also is able to be leveled, but there's no fixed point, so the whole platen is kind of free floating on a pivot. So there are these 3 screws, and then they go into compliance brackets, so they go into similarly cut tabs like this, which have a bit of compliance in them to allow for leveling of the lower platen. I'll talk you through leveling later. We've got 2 different jigs, well, there's three different stages to leveling, which I'll go through later. Wafer clamp pressure control system. Right. This machine is equipped with a pressure control system, so we can control the pressure from anywhere down to 1 to the minus 5 millibar up to 2 bar overpressure. There are 4 different vacuum and overpressure gauges to control that, and it's accomplished via the software, via a PID loop in the software, which controls that valve down there. So nitrogen goes into that valve through this line and comes out through the top line there. There's a needle regulator inside that valve. The position of that needle is controlled via the PID loop in our software, and it will enable fairly accurate pressure control. Oops. Alright. So when we want to use pressure control, we can set a pressure in here, switch the system on and off. The software will then take control of the process to control the pressure. So what it will do, it will slow the turbo pump down, because if the turbo pump is spinning at maximum speed, any gas that we put into chamber is going to get pumped out immediately. So we slow it down to about 55 or 60% of its full operating speed, and then admit the gas. The software takes control of all of that automatically there. So all you have to do is tell it what pressure you want and switch it on. But that's how it works. RAD system. So the RAD system, RAD is short for radical activation. It's basically the plasma system, which this machine is also equipped with. So the plasma is generated inside this ceramic ring here. There's an electrode in the center that you can't see underneath this top ceramic in the middle. That has a negative voltage applied to it of 500 volts. Excuse me. And these 2 outer electrodes are grounded. So the plasma is generated in between the driven electrode and the grounded electrodes. Radical species are produced inside this ring, and then they just sort of float out through the perforations and bombard, well, not bombard, but hit the wafer surface. The idea of it is not to bombard. We don't want to sort of etch the surface or roughen it. We just want to activate it. So they're free radical species, reactive. They create reactive sites on the wafer, which then lowers any activation barrier for direct bonding. We don't know exactly how that mechanism works, but we know that it does take a pragmatic approach. When using this plasma system, that's probably when you're going to get wafer dehydration potentially. So if we do a very long activation, if you leave it under vacuum for half an hour, typically we'll operate the plasma at about 1 millibar. So if it's left under vacuum for a long period of time, any hydration, any moisture on the wafer surfaces will become dehydrated. That's when we need to use this water injection system to rehydrate them before we can, so that we can achieve a bond. HT system, high voltage system, I've kind of touched on that already. That's applied to the support ring through this wire here. Control, I'll talk you through this when we go through the software operation, but essentially we have a target voltage and a target current. Generally speaking, the process will start off in current limiting mode. So it will just draw whatever voltage is needed to maintain the current limit that you set. So as the bond progresses, the voltage needed will get progressively higher and higher. And then eventually it reaches a crossover point where we reach the target voltage, and then the current will begin to decay after that. we'll see that during the bond. It's all displayed graphically on here, and then there's a toggle switch for turning it on and off. The plasma system is kind of more simple. It's for this 4-inch system that we have here, 500 volts, 100 milliamps, they're the default parameters, that's all you need to use really. You can reduce the current if you want to have a less intense plasma for any reason, but generally we found that those default parameters work well, so they're there for default. So all you really have to do is achieve 1 millibar using pressure control and then switch it on. So for like the behind the scenes is fairly complex, but in terms of usability it's fairly simple. That's the idea anyway. Lastly, the DB pin. Actually, I'll show you that with the lid open. So on the top side of the lid, we have this cover here. Attached onto that, there's a ceramic pin tip that's going to, when we screw it in, there, we should be able to see under the wafer in the center there's a little ceramic pin tip. The idea, when that's screwed fully in, the pin tip will protrude by approximately 100 microns. And the idea of that is to bow the wafer slightly in the center. So then when we bring the lower wafer up, the center makes contact first, and then the bow is flattened out. So we achieve center outward bonding. So we start the bond in the middle, and the wave propagates outwards towards the edges. And also that helps to hold the upper wafer, helps to hold the wafer steady. So when you make contact, it prevents any kind of shift in the alignment